In this talk, I will introduce a tool named OptiROP, which let you find the ROP gadget for ROP programming like you can never do before. So it's kind of innovative tools for you to program your ROP shellcode. Okay, so the motivation behind my talk is that ROP programming is very hard, but all the current ROP tools are not very helpful. You must still find the ROP gadget yourself, and you must still change the ROP gadget yourself manually. So nothing can help much. And to fix the problem, I come up with a tool named OptiROP. And the core idea of OptiROP is to build around the semantic query. So you can look for the ROP gadget using semantic queries rather than syntactic query. And so in this talk, I will first take a short discussion on the background of ROP gadget and ROP shellcode, and I introduce a problem on the current ROP tools. And next, I introduce the OptiROP, the ideas behind this tool, the design and the implementation, and there are a lot of live demos. Okay, so first, software attack. We will know that attacker abuse the software flaws to exploit the application, and they trigger the vulnerability with malicious input to execute the attacker's code. And to defend against software attack, people introduce many exploitation mitigation. So the idea is that we accept that the software can be buggy, but we make it very hard to exploit the bugs if that happens. And people introduce many mitigation mechanism, but on this talk I focus on data executable prevention, or DEP. DEP is very widely deployed nowadays. It makes sure that input data from the attacker is unexecutable. So the input cannot embed the malicious payload inside anymore. And DEP was introduced into the hardware level and present in all the modern system nowadays. So DEP is everywhere. However, DEP is not perfect. To bypass DEP, people introduce return-oriented programming techniques, or ROP in short, and ROP can be used to defeat DEP. So the idea is that ROP is that it makes sure the attacker is not needed to be inside input data anymore. So you can defeat the DEP-based defense, and the ROP becomes the main technique to write shellcode nowadays. So the concept of ROP is that we don't use code injection anymore, but we use available code in exploited memory space of the vulnerable application, and we abuse a code snippet, or we can call that ROP gadget, and we change all the ROP gadget together to execute some actions that we want. And ROP gadget mostly come from unintended instruction, and people already prove that ROP is Turing completed, which means you can change the ROP gadget if you have enough gadget to do whatever you want. So here's one ROP example. In this example, we have some ROP code inside the stack memory. Stack go from top to bottom, and you can see here we have this gadget, and this gadget, and something inside the stack. So if you can jump to here, this instruction will be executed. So pop EDX will pop out FFF EDCC, right? So after this, EDX become FFF EDCC, which actually is -1, 2, 3, 4, right? And after that, we return to here, which actually executes some instruction in the memory, which is store EX, and return. So after this, EX becomes 0, right? And we return to here, which execute another instruction, sub EX, EDX, and red, which subtract subtract EDX from EX, because now we have EX, we have EX is 0, and EDX is minus 1, 2, 3, 4. So after this gadget, we set EX to 1, 2, 3, 1, 2, 3, 4, right? 0 minus 0 subtract minus 1, 2, 3, 4 from 0. We have 1, 2, 3, 4. Okay, so we have many ROP gadgets. We can change them together to achieve the traditional code injection shellcode. So you can write the traditional shellcode using the ROP gadget by chaining them together. And usually the ROP shellcode, usually it is implemented as a stage 0, which then remap the stage 1 memory to be executable. And after that, we change the control to the stage 1. So we can see that actually ROP shellcode is just to execute the first stage. However, you can see that ROP shellcode, we can see that it dominates the future, because nowadays the modern system put more and more restriction on what ROP gadget can do to launch the next stage. For example, in Windows 8, they introduce some mitigation techniques, so they enforce the policy who and where can call virtual unlock and virtual protect to enable memory executable. So it's very hard to call these two functions on Windows 8. So which means Windows 8 push the exploitation writer to do more work in stage 0. And I can imagine that in the future, the modern future system can totally forbid the code injection. So no more stage 1, but we have to do everything in stage 0, which means we need to have full ROP shellcode. No more stage 1. And actually, iOS already implemented this mitigation, because they set the writable base to be non-executable, and only side base are executable, which means ROP is the only choice for shellcode. So the shellcode in iOS must be fully ROP. No more traditional shellcode. So we see that ROP programming is very hard, because you need to find the right gadget to change them to do what we want. And you can see the full ROP shellcode can be a nightmare. Very hard, take a lot of time to do, to implement the good shellcode. And however, we can use the ROP tools to help your shell to find the right gadget and change them. However, the current ROP tools are not very helpful, because what can they do is that given the binary containing the gadget at runtime, the ROP tools that collect all the gadgets available in the binary, and after that it can help us to find the right gadget from the collection. However, mostly all the tools stop here, and nothing can automatically find the right gadget, and nothing can help us to change them automatically. We need to find the gadget ourselves, and we need to change them ourselves. Nothing can help. So everything must be done manually. So it's very tedious, very boring at this stage to write the ROP shellcode. Okay, so here's some high-level gadget. We have few type gadget like load, store, adjust, clone, and sysclone. For example, load can load value to register. For example, this gadget can copy EBP to EAX. This one copy D7 to EAX. This one copy value in the memory into EAX. Store, similar. We can use this gadget to copy EDI to memory. This one, some concrete value to memory. Adjust, adjust the register by a constant or by a register, and we can use a clone gadget to clone one function, and finally the system clone gadget can be used to execute the system clone. Okay, so here's what all the traditional ROP tools do inside. They do two things. First, they get their own gadget. To To do that, they locate on the return instruction, and after they walk back few bytes and look for legitimate sequence of instruction and save them. So for example, here we find the red instruction, and if we come back 3 bytes, we have a gadget that is 3 instruction. But if we come back 4 bytes, we have 1 instruction, and so on. So that's how all the ROP tools locate and get all the gadgets. And the second thing ROP tools help us to do is that we can give the ROP tools some questions, and it can help us to search and to look for the suitable gadget. So basically, the ROP tools go through the list of all the collected gadgets and match them with the request from users. But mostly, this one is important, mostly they only use regular expression searching on the gadget text. That's what they do. Here's one example from a very nice tool named ROP. So you can see here, to find all the gadgets that copy something to EAX, they give we give ROP the query like this: move register 30-bit register and something behind. So we have the return like this. Everything is about copy something to EAX. So you can see that this kind of searching is very typical in all the ROP tools. They use some very simple syntactic searching, some regular expression searching, right? So the problem of all the tools is that syntactic searching is very easy to implement and is a universal solution and proven. So all the ROP tools implement this syntactic searching, mostly based on regular expression searching. But the problem is that the result from the search is not complete, which means ROP tool don't find all the gadgets for you. Second, it don't find everything, but it can miss something. Next, it might return many irrelevant gadgets, which means those gadgets that's not helpful at all, cannot be used. It's very time-consuming use ROP tools nowadays because you need to repeat trial and error, repeat with different searching query to find the right gadget for you. And sometimes because we don't have many gadgets, so we must use them properly. But all the ROP tools currently cannot help you to do that. So I show you some problems on the ROP tools now. First of all, you want to find the gadgets that copy EBX to EAX, which means you want to have something like this. EAX be equal to EBX after the gadget, right? So the factor answer is that we do many syntactic searching, mostly based on regular expression. For example, we search for something like this, copy something to EAX, and hopefully we have this gadget, right? If we don't find anything, we try another question. Exchange EAX with something, and hopefully you have exchange EAX with BX as a return. But if you don't have this, you need to go to the next question. Load effective EAX with something, and hopefully you have this in the return gadget. So, to find one gadget, we need to try many questions. So the first question is that, do we miss something? Do you miss any promising searching question here? First one, we miss this one. Exchange EAX with something, we miss this one. This one set EAX to BX, right? So we miss this one. We miss this one as well. Multiple EBX with one and assign that to EAX. We miss this, right? So you try many questions, but we still miss something. And anything else still missing? I don't know. Maybe people with more experience can tell me. So the question 2 is that how many queries and effort do we need to find this simple gadget? Probably many. A lot of effort, a lot of time. Okay, the next questions. We still need to find the gadgets that copy EBX to EAX. Now, can you tell me which syntactic query can find below gadget? This one. So EX, EX, which means 0 RBX, right? And after that, pop ESI. And finally, 8 EX with 8 EBX to EX and copy to EX. This one actually assign EBX to EX because here we have EX is 0. Now can you tell me which syntactic query can find this? Nothing, right? Because what we do is a semantic. We have the semantic gadget here, which means you need to understand how it works inside, not how it looks. And this one, so EX with itself and not EX, which means we have EX is -1 here, right? And finally, N EX with EBX, which means copy EBX to EX. So this one also copy EBX to EX. But can you tell me which syntactic query finds this? Maybe nothing. This one, exchange EBX to ECX, which means copy EBX to ECX. And next, exchange ECX with EAX, which means copy ECX to AX. Because we have ECX is equal to EBX here. So finally, you have EAX equal to EBX after this gadget. And no syntactic query can help me to find this. And finally, push EBX, and after that, later pop EX out. Also copy EBX to EX, but syntactic query cannot help. So another question. We need to find the gadget that pivot, which means migrate stack to somewhere that is under our control. So the ROP tool suggests all the following questions. Searching for exchange ESP with something, exchange some register with ESP, and something with ESP. You can whatever instruction. And after that, we need to look through all the return gadget to decide which one is good, which one is the right one. So any missing thing here? Any missing query here? We miss this one, right? Copy EBP to ESP. So we try many things, but we still miss something. So the other problem is that on the current ROP tools, you can see that nothing can report the semantics of the suitable gadget, which means it returns a lot of gadgets, but nothing can tell me the semantic of each gadget. For example, nothing can tell me which register is modified in this gadget, which effects is modified in this gadget, and how many bytes the stack pointer is advanced after this gadget. Nothing can tell me. It only returns me the raw text of the gadget assembly. And more importantly, no tool can change available gadget for the requested semantic gadget. For example, nothing can return this. You can see here we can combine two gadgets and change two gadgets together. Change saw EX, EX, red, and exchange EDX, EDX. Because this one make EX 0. So this one copy 0 to EX, which is 0 to EDX. So finally, you have EX is 0. So you can see that no tool can help me to change available gadget to do something I want. For example, I want to assign 0 to EDX here. No tool can help me to find these two gadgets and combine them together. And this one also, this one actually copy -8 to ESI, right? And change that with this one. ESI is -8, so ESI plus 8 is 0. So effectively you have EX is EDX equal to EDX here. And no tool available can find these two gadgets and change them for me. Nothing, absolutely nothing. So, because everything sucks, so we need to have some solution. And I came up with a tool named OptiROP, which can help you to find the gadget like you can never do before. So here's what I want for the OptiROP. First, I want to do semantic searching rather than syntactic searching. So the idea is that the semantic query, I use semantic query rather than syntactic query, which means I rely on the meaning of the gadget, but not how the gadget look like. Not syntactic, but semantic. For example, here's my semantic query. EAX equal to copy the value in the memory pointed by EBX to EX. And this query can return these two gadgets. Sorry, this one should be inside the mark here. And this query, ESI equal to EDI, which means I want to copy EDI to ESI. This one should return these two gadgets. Right? So the idea is that I want to use semantic query, which specifies the semantic meaning of the gadget. And OptiROP should return me everything that match the request. Second desired one is that OptiROP should allow me to specify some option so I can filter out the gadget return. For example, I want to specify I only want the gadget that modify this register and don't modify this register. And I want to limit the amount of stack pointer advance after this gadget. I don't want the stack pointer to advance too much, for example. And the third request is that I want OptiROP to provide all the detailed meanings of the file gadget. For example, if OptiROP returns this gadget, it should tell me that this gadget modifies this register, EAX, and those E-flags. And it should tell me that ESP is advanced by 80 bytes after this. So I want to have detailed semantics. Third one, I want OptiROP to help me to change all the selected gadget if the natural gadget is not available. Which means if you want to do something, but in the setup gadget we don't have anything like that, I want OptiROP to find the gadget and change them to do that for me. So the last the chain available gadget is very important, and that can help a lot. And finally, I want to support a lot of platform, 32-bit and 64-bit, and on the modern system. You can support it should support Windows, Mac OS, and Linux, and even raw binary. Okay, so you can see that all the other tools available now is here. They can only get the gadget, and they can do some syntactic searching, and some tool can do very simple semantic searching. But OptiROP should go further. We should do the same thing like gathering gadget. We can do syntactic searching. We should do very good semantic searching, and finally we should be able to change gadget together automatically for you. So we can compare OptiROP with some very popular tools here. So like here, nothing can do semantic query except immunity debugger. But immunity debugger can do very basic function to change to do semantic questions. And nothing can change the gadget. And OptiROP should support everything on the platforms. Immunity debugger is very nice, but they only support 32-bit of Windows now. Nothing else. And that's my target, my dream. I want to build something like this. Okay, so next we come to the semantic query. Here I define the semantic query for OptiROP. First of all, for load type, I should be able to specify the semantic query like this: EAX equal to EBP, and OptiROP should find all the gadgets that copy EBP to EX for me. Right? You can see all these three gadgets copy EBP to EX. Store copy EDI to the memory at EBX, and this semantic query should return these two gadgets. As that, we advance ECX by 5i, and this query should return these two gadgets. This one actually, what's that? Okay. This one is minus 9, so which is subtract minus 9 from ECX equal to 8, 9 to ECX, right? And so on. So OptiROP should be able to process the semantic query and give all the gadgets that it can match the semantic query. So the idea behind OptiROP is that we build everything around the semantic query, and we use semantic logical formula. And internally, OptiROP generates the semantic logical formula on the gadget code. And after this, OptiROP allows semantic query. So we can describe the high-level decision for the gadget by give it the semantic query. And OptiROP should be able to perform searching semantic query based on the logical formula using SMT solver. And OptiROP can combine logical formula to change the gadget to produce the desired semantic actions. So there are some challenges. Machine code, for example, in Intel platform, machine instruction really overlap. You can have many instructions but do the same thing. For example, these two instructions here, actually they do exactly the same thing. And the instruction can have multiple implicit side effects. For example, boost instruction actually does many things inside. It copy register into the memory, after that decrease the stack pointer by 4. So we need to understand the semantics of the instruction, right? So what we need to do is that we need to normalize all the machine code to some intermediate representation language. And the intermediate representation, or IR, must be very simple, no overlap. And IR should express the semantics explicitly without side effect. And IR should support static single assignment. This one is important for the step of generating logical formula. So the idea is that we need to normalize the machine code, and after that we optimize it. We translate the machine code to some intermediate language. After that, we optimize it to make it more compact. And finally, the output of this step will be sent to the next step. And the next step here will generate the logical formula from the optimized IR. So the question is which IR I should use. And here in this project, I use LLVM. LLVM is one open source project originally introduced to build compiler for you. And it consists of a set of framework to build compiler. And LLVM is built around one intermediate language named LLVM IR. And on top of LLVM IR, there are a lot of optimization modules ready to use. So here is the model of LLVM. So we want to compile some high-level language. We use the LLVM front-end here. And LLVM front-end will translate the language, the source code, to LLVM IR. And LLVM IR will be sent to the LLVM optimizer, which optimizes it. And this step can make the code much smaller, for example. And after that, after this step, we have the LLVM IR already optimized. And finally, the backend will compile the LLVM IR to the native code. That's the model of the LLVM framework. So the idea is that the LLVM IR is something very simple, independent of architecture. And it's kind of register-based machine with unlimited number of virtual register. Register can have high-level type like float, integer. It can have pointers. It supports single static assignment by nature, by default. And when you compile from source code to LLVM IR, we have LLVM bitcode. And there's some, at least here's some instruction for you, LLVM instruction. So LLVM has very small number of instructions, only 31 instructions. And they have instruction to add, to do arithmetic operation, to do bitwise, to branch, and to access to memory, things like that. So it's quite similar to the low-level assembly. And here's an example. If we compile the code on the left side from C code to the LVM, we have the code on the right side. And the code on the right side is in LVM IR, which does the code on the left side. That's in C. Okay, after the front end, we send the LVM bit code to the optimization, and optimization can help you to optimize the code to be much smaller, much faster, for example. And there are a lot of optimizer already available in LVM, and you just need to use it. You don't need to do anything. So why I choose LLVM IR? Because this LLVM is very good for normalization phase. And they already provide a handy framework so you can process the output IR very easily. And finally, we can just use available optimizer in LLVM to optimize the output after you translate the machine code to LLVM. So there are many advantages, and that's why I choose LLVM. So see how it works in the normalization phase. I translate the machine code to LLVM. After that, I send the output, which is the LLVM bit code at this stage, to LLVM optimizers. And you can help me to optimize the code to be something still in LLVM form, but smaller and more compact. And here's one example. On the left side, you can see one Intel instruction. And on the right side, I translated that instruction to the LLVM IR. And you can see the code on the right side is actually quite longer, because we need to express on the implicit semantics of the Intel instruction. For example, you can see here we have a lot of instruction to update the flag register, the E-flag registers. Okay, skip some slide, not very important. So here is one example. On the left side, on the yellow block, we have the machine code, and we compile this machine code to very long code in the pink block. And after this, I optimize the code in the pink block and have something very simple here. Why? Because here you can see the machine code here. Sort EX with each cell. After that, exchange EBX with each cell. Exchange EBX with each cell actually does nothing, right? This one is that instruction. And add high to EX, because after this EX is 0. So finally, what this code does is simply copy true to EX, right? And that's why the optimized code is very short. So you can see the optimizer in LVM is very, very nice. You can do the automation very well. Okay. Next, because we use SMT solver in this project, so I introduce briefly about SMT solver. So SMT solver is kind of theorem prover based on the decision procedure, and SMT solver can work with logical formula on different theories. And most importantly, SMT solver can prove the satisfiability or validity of the logical formula. You can tell me that the logical formula is right or wrong, true or false. And in the case the formula is true, you can tell me the context, in which context the formula is true, and so on. And more importantly, SMT solver is SMT language is very suitable to express the behavior of the computer program. So in this project, I use Z3 SMT solver, which comes from Microsoft. Very nice project, open source, support Linux and Windows, have binding for C++ and Python. Support bit vector theory, so can model the arithmetic and logic operation. Support array theory, so can model memory access. So here's how we generate the logical formula from the machine code. For example, here's some malware like this. Copy 48 to ESI, copy 207 to EDX, and you have the logical formula like ESI equal to 48 and EDX equal to 207. It's easy, right? This logical formula express what this code does. And here, in case we have control, we have the control flow inside the machine code, we need to consider that for branches. Like here, we have 2 branches, jump if equal to somewhere, so we need to express the semantic of the branches here, the 2 branches. Okay, so next step is that we need to generate the logical formula from the LVM-IR. So the idea is that we translate the machine code to LVM-IR here. After that, we generate the logical formula from the LVM-IR. How does it work? I need to roll one LVM pass to translate the bit code to SMT logical formula. And I need to go through each instruction in each LVM block, basic block, to translate each instruction to LVM, each LVM instruction to SMT formula. Okay, so now you can already generate the logical formula from the gadget code. The next stage is that we look at the OptiROP model. So OptiROP has 2 phases. The first phase is like on the traditional ROP tools. We need to prepare to get on the gadget. This stage. And the next stage, we come to do the main thing that we want to do. You can search for the gadget on the collected gadget in the first phase. The first phase is done in traditional way, like on the other ROP tools. We locate the red instruction, and after that we walk back to collect on the legitimate sequence of instruction, and we say on the gadget we found. So there's nothing special here. Second stage, for each gadget code which is assembly form, we generate one SMT formula for that. So with each gadget we have assembly code for the gadget, right? So I normalize the code. After that, I optimize it, and finally, I generate the SMT formula from the optimized LVM-IR, as I explained in the last few slides. And you can see here that I build OptiROP on top of the framework, which consists 2 layers. The bottom layer normalize the code for me, and after that, optimize it. The middle layer generates the logical, the SMT formula for me. So OptiROP is built on top of these 2 layers. Okay, so there's one thing I need to do in this stage. Which each gadget I need to save. You need to say on the modified register of the gadget and on the stack pointer how much stack pointer is advanced with each gadget. And here is how I calculate how much the stack pointer is advanced for each gadget. So the idea is that this time I ask the SMT solver to tell me how much is the difference between the final value of the stack pointer and the first value of stack pointer. So this consists of 2 steps. Is it easy to see from behind? Okay, I have gadget like this. Copy, move EBX to EX and return, but with 12 bytes. And I generate the logical formula from this gadget, right? It has a SMT formula like this. And I add one variable named diff. Diff is the difference between ESP1, which is the final value ESP of this gadget, subtract minus to the first value ESP1. And I ask the solver for the model of this SMT formula. This one is always satisfied. SMT solver can always find the diff value, right? For example, here it returns the diff is 16, which is strand 22 in decimal mode. and I generate another formula, which is, this time I ask if ESP1 minus ESP can be different from 22 or not. And again, I try to show this formula. If this one is set, unset, this one should be unset, which means ESP is advanced. The value of ESP advanced is exactly 22. But if this one is set, we can know that ESP advanced is unknown. We don't know how much ESP pointer is advanced after the gadget, because sometimes the ESP change, and that depends on the context. So we don't always know. Okay. Now we look into the gadget. Because the gadget mostly evolve around the register and require register, so we classify we try to find all the gadget based on primitive gadget. And the primitive gadget is classified to two types, the P1, P2. P1 is a gadget that set register to another register. For example, this one is a primitive register of type 1. This one copy EDX to EX. P2, the gadget that set register to immediate to some constant. For example, this one. This gadget copy 0 to EDI, and after that, this one copy EDI to EX, which means make EX 0, right? So this gadget make EX 0. So this one is a P2, set 0 to EX. This one set one register to another register. This one set one constant to one register. So we need to find all the primitive gadget from the set of collected gadget. Okay, so again, I classify the primitive gadget into two types. First one is natural gadget. Second one is chain gadget. It's a natural gadget. We just pick the gadget as is. We don't do anything. Gadget is there. We take it. And it's a natural gadget. We classify it into two types, PN1 and PN2. PN1 set register to another register. This one, for example. PN2 set some constant to register, like this. And the third one is free register gadget, which means we can set any value to one register. And on this register, I use a pop gadget, which set register to the value popping out from the bottom of the stack. So we can freely get any constant to the register, for example, here. This one pop EAX from the stack memory. So we can push something, can be anything into the stack, and after that it pop it out. And this one can set EAX to anything you want. And this type of gadget is very important. Second one is chain primitive gadget. This type of primitive gadget should help me to chain different gadgets together, combine them together, so I don't need to do that manually. So again, I classify the chain primitive gadget to three types: PC1, PC2, and PC3. PC1 copy one register to another register, like this. This one copy EDX to ECX, and after that copy EDX to EAX. Oh, sorry, there's one mistake. Should be EDX here, ECX here, and this one finally copy EDX to EAX. PC2 copy constant to one register, like this, or EBX with FFFF, so which make EBX FFF, right? And after that, exchange EBX with EX, and finally we have EX equal to FFFF. So third one, which is very interesting, we have gadget that derive from computed equation, and this one we require the constraint to achieve the target gadget. For example, here, this one, what it does, multiple 0 with something and copy to ECX, which mean copy 0 to ECX, right? And here, add EAX to ECX, because ECX is 0, so After this, you have ECX equal to EAX, right? This one, we have some computation. So you need to have some computation, and how to do that is the question. Okay, so the first one, P1. P1 is to find origination, that's it, that copy one register to another register. So what I do is that I generate the SMT formula from the gadget. And after that, I try to prove if this gadget is equivalent to another gadget. And this case, I want to prove that ESI equal to EX, right? So I generate the SMT formula for this one, and I add another formula here, ESI equal to EX, and I try to prove G and F are equally. And if this works, I can tell that ESI equal to EX after this. If this one is unset, ESI is not equal to EX. That's a PN1. Okay, here's a demo. Okay, so here's the demo of the OptiROP. This demo I catch it from one binary in the Linux, and I collected everything on the gadget, on the SMT formula for each gadget, and now I can show you. Here's the question. Can you see that? This one is a file that contains all the gadgets I collected. And what I want is that I want to find all the gadgets that copy EDX to AX. Right? Okay, so a lot. Some are very trivial, but some are very interesting. For example, this one. This one copy EDX to EX, right? And this one modify EX register, of course. And this one advance the ESP by 4 bytes after this. Another one, this one. Exchange EDX to EX, so copy EDX to EX and return something. What is interesting here? Okay, you can see a lot of gadgets, but they all do the same thing, copy EDX to EX. Okay, the second type, PN2, copy constant value to register. So this one is a bit different. Like this gadget. Copy 0 to EDI, and after that, copy EDI to EDX, which means copy 0 to EX, right? So this gadget is set 0 to EX, right? So I generate the logical formula, the SMT formula. And after that, I add something. I try to find if this one has constant value. So I try to find the model of this one, and this one return the result, tell me that EX is always equal to 0 after the gadget. And I can check that again. I can insert another formula here. I ask SMT solver if EX can be different from 0 or not. And again, I feed it to the SMT solver. If this one is unset, which means EX is always 0. If this one is set, EX can be different to 0. It depends on the context. But in this case, EX is always 0. So, here's another demo. Again, I run OptiROP, and I want to find all the gadgets that copy 0 to EX. See? A lot of different things. And here something very interesting. This one. You can never find this one with syntactic searching.
copy 0 to EDI. After that, copy EDI to EAX, which means copy 0 to EAX. So this one really copy 0 to EAX and modify EAX and EDI registers. And advance the ESP by 8 bytes because we pop something out here. Right? And everything else, you can see, everything else, set 0 to EAX. They look differently, but they do the same thing. Right? Okay, next one. Okay, change gadget. I can change the gadget together because with available gadget, you can change them and you can have PC1, PC2, and PC3 here. So the idea is that PC1, PC2 copy the register to another register. PC2 copy constant value to another register. And the idea is that if we have R2 equal to R1 and R3 equal to R2, you can combine these two together and we have R3 equal to R1, right? So the idea is that we find two gadgets. Just set register to another register and can combine them. So how we can do that? The idea is that I use some very simple graph theory algorithm, and I build a tree. In the tree, one node is connected to another node with the first node can be equal to the second node. For example, here, if EAX can be set to EAX can be set to EBX, EDX, ESI, EBP, I connect them. And because EDX can be set to EDI, ECX, and some constant, I connect EDX with EDI and ECX and constant. And you can see, because there's a path from ECX to EDX to EAX, so EAX can be set to ECX, right? There's a path, so you can bridge them. And because there's a path from constant to EAX, so you can set constant to EAX thanks to this gadget and this gadget. You can bridge them. You can jump from one node to another node. And each jump is one gadget. So here's one demo. Okay, here's one demo and you can see how effective this is. I try to find all the gadgets that copy EDX to ECX. Nothing. There's no gadgets that copy EDX to ECX. Now, I try to change them. Still the same question, but I change them with one parameter C, which means change. I want to find the gadget automatically and change them to copy EDX to ECX. Because the natural gadget cannot do that. Just no natural gadget can do that for me. Okay, a lot. See? This is possible because we can change gadget together. For example, I have two gadgets. This one, copy EDX to EAX. And the second gadget, exchange ECX with EAX. And this one, because copy EDX to ECX, and after EAX is exchanged to ECX, so you have ECX equal to EDX, right? So you can find gadgets that don't do it, but by combining them, we can do that. My time is already running out, so probably I should just focus on demo. Okay, you can read the slide later. This one. Again, I try to find all the gadgets that copy EDX to ECX, and here we have some complicated computation. For example, we insert something to 0 to stack memory, and this gadget pop is CX out. So after this, we have ECX is 0, right? And the next gadget, because ECX is 0, so add EDX to ECX makes ECX EDX, because ECX is already 0, right? Can you work out that? So you can see you can do some very complicated computation here, and you can change few gadgets together, and you can even insert something into the stack memory and pop it out, doing something very complicated. But finally, we achieve what we want. Anything interesting here? Okay, this one is interesting. This one is interesting. Maybe it's the last demo. Oh, sorry, too fast. I want to find all the gadgets that advance ECX by 14 by. See, because there's nothing that advance ECX by 14 by. OptiROP find two gadgets for me and change them. The first one, advance ECX by 4 by. The second one, advance ECX by another 10 by. So totally, we advance ECX by totally 14 by, right? So you can see OptiROP is very, very smart. Finally, because I'm running out of time, I'll show you another thing. So what I saw so far is that OptiROP come in the command line form, but I already built web-based for OptiROP. So here we go. We want to find all the gadgets that set 0 to EX. Search. So it take some time, so please wait, like few seconds. Okay, so we found totally 22 gadgets, and everything copy 0 to EX. I put everything together into one web form. Okay, so here is that this one. This one modify ESI, right? So modify ESI, pop ESI, but I don't want any gadgets that modify ESI, so I want to preserve that. Okay, I want to find all the gadgets that set 0 to EX and preserve the value of ESI. So I input that here. I can also specify how much stack memory is advanced after the gadget, but I leave it blank here. Search again. Okay, this time it filtered out 7 gadgets and it returned me 15 gadgets, only 15 gadgets. And everything preserve ESI. Okay, come back to slide. Actually, I don't skip much, so still not too bad. I had some trick to. I did a lot of tricks to improve the performance of OptiROP here. You can take a look at the slide. A lot of tricks, interesting. So currently in the OptiROP, I implemented the web and command line interface. I have few framework to translate machine code to LVM, generate the SMT formula from the LVM bit code slicing, which you can see the slide. And OptiROP at the moment support on the 32-bit and 64-bit platform of Intel with all the own kind binary. It can be Windows, Mac OS, or Linux, or even raw binary. Conclusion: OptiROP is an innovative tool to find ROP gadget for you. It can support the natural and easy semantic questions. We don't rely on the syntactic question anymore. Internally, we use compiler techniques, LVM, and SMT solver to solve many questions. And OptiROP, importantly, it can change the static gadget together. If there's no natural gadget can do what you want. And this tool will be introduced to the public very soon. because currently there's still bug fix. This is still bugs I want to fix. So please wait, and you can watch out for this arrest. When I release this tool, it will be at this arrest. So finally, here's one. I summarize the features of OptiROP compared to other OptiROP other ROP tools. Yes. So any questions? Sorry? Okay.
You could use the mic, right, but the bugs will have to repeat the question. Can you just go back to the slide with the URL?
Which slide?
That one more. This one right there.
This one? Yeah. Yeah, I want to develop more methods to chain gadgets together. I want to introduce higher level gadgets rather than only few types like what you saw. I want to do full compiler-based implementation. It should be do more than that. I want to support ARM. Because now OptiROP only support Intel platform.
How are you going from assemblies or LLVM?
Sorry, can you?
How are you translating from assembly, x86, to LLVM?
Okay, I have one slide here. The question is how to translate machine code to LLVM.
What tool are you using?
I be waiting myself from scratch. So here, this slide. So basically, what I did is I built something like compiler front end, but for machine code language to translate machine code to LLVM. So I need to work out. I need to analyze the machine code and work out on the control flow graph consists of basic block, and I translate each basic block to LLVM. And inside each basic block, I translate each machine instruction to LLVM. And that's how it works. And for this step, I need to reference the ISA manual on the platform, like in this case, Intel manual, to understand on the semantics of each instruction, so I can translate properly. ARM disassembler. ARM dis. Okay, disassembler, because yeah, actually I use to say some work. I don't translate directly from machine code to LLVM, but I translate the machine code back to assembly. So I use some assembly, some disassembly here. So I translate, what I did is that I translate machine code, native machine code to assembly, and after that I translate assembly to LLVM. And that's how it works. So I don't need to understand how the disassembly work inside. And for this, because of this, I can very easily translate 32-bit and 64-bit to LLVM. I don't work at the low level, but I use some assembly disassembly. Yeah. Okay, this project is pretty. This one is actually not trivial, and okay, this one slide. I mainly use Python and C++ to do on the programming, and this project take around, I think, like around 10,000 lines of code. So it's not trivial at all. It takes a lot of time to work. Okay, that's a good question. I have one slide for that here. Where is it? Okay, this one. Actually, LVM has 31 instructions, but I don't use everything. I only use subset of those instructions because inside LVM they have some instructions that work for high-level information. So you can translate the high-level source code to LVM, and those instructions that contain the high-level information in the source code I don't need. Every instruction that contain high-level information, like pointers, or yeah, I can show you later. But basically, I think I use only like maybe 20 LVM instruction. Any more questions? Sorry? This takes some time because there's still many things I want to do, so maybe 1 or 2 months. I'm not so sure now. Yeah, but I want to push it out as soon as possible. So no more questions? Thank you very much.